Hello and welcome to today's lecture on the basics of semiconductors. In this video, we will discuss the fundamental concepts that supports modern electronics. Especially, semiconductors are considered to be the building blocks of devices we use every day. We can find it from smartphones to computers and even in solar panels. So, let's get started. This is the outline of this presentation. Now, let's understand what semiconductors are and why they are so crucial in today's technology-driven world. Let us start with an atom. So, an atom is the smallest unit of matter that retains the properties of an element. So, atoms are incredibly tiny, making up everything in the universe, from the air we breathe to the stars in the sky. So atoms consist of three primary subatomic particles, the protons, neutrons, and electrons. So if we zoom in a gold atom, so we can observe that protons and neutrons are they reside within the nucleus at the atom's core. So this is the nucleus, and the electrons encircle the nucleus. They encircle the nucleus in electron clouds or in energy levels. So later we will learn about the atomic model. And for the electrons, electrons are negatively charged particles. Again, it orbits the nucleus, and the number and arrangement of electrons in these energy levels determine the atom's chemical properties. Okay, while the protons are positively charged particles, and each element has a unique number of protons in its nucleus, and this defines the element and gives its atomic number. Lastly, the neutron. So this is the neutron. The neutron are neutrally charged particles, so they have a relative charge of 0 or neutral, and they help stabilize the nucleus and determine the atom's isotope, and which can vary in the number of neutrons, and the balance of protons and neutrons, electrons rather. It determines the atom's overall charge. So when protons and electrons are equal, the atom is neutral. So meaning it changes in this balance, the changes and in this balance leads to ions with a positive or negative charge. Now we will take a journey through the history of atomic theory, exploring how our understanding of the atom has evolved over the centuries. So let's start with the Greek philosopher Democritus, who introduced the concept of the atomos, meaning this is the indivisible particles that make up matter. Although his ideas lack experimental evidence, they laid the foundation for future atomic theories. So jumping ahead to the early 19th centuries, so we have John Dalton. So his atomic theory is called the solid sphere model. And he suggested that atoms are tiny, indivisible spheres, each with a unique mass. However, Dalton's theory was revolutionary, and it provided a framework for understanding chemical reactions. So while in the late 19th century, we have J.J. Thomson. The experiment of J.J. Thomson is that he experimented about cathode rays, and this led to the discovery of the electrons. Okay, the electrons, the negative charge particle, and with this discovery shattered the idea of indivisible atoms, and introduced the concept of subatomic particles. So from the solid sphere, which is indivisible, here comes Thomson that said that he introduced the idea of electrons, and his model is called the plum pudding model. Next is we move forward to the early 20th century with the Ernest Rutherford's gold foil experiment, and it revealed that atoms have a tiny, dense nucleus at their center. This one. And it is surrounded by mostly empty space. And this marked a significant departure from Thomson's model and brought us closer to the modern understanding of atoms. While Niels Bohr model, so he proposed this model in the early 20th century, and he introduced the idea of a quantized energy levels for electrons. So here we have the energy levels, and this model explained the atomic spectra and formed the basis for our understanding of electron behavior within atoms. In the early to mid 20th century, we have the quantum mechanical model, and it incorporated the wave particle duality of electrons. And this model provides a comprehensive understanding of electron behavior and is the foundation of modern atomic theory. Now, what are semiconductors? So, semiconductors are materials with properties that lie between those of conductors. So, we will have our pen. So, those of our conductors. So, these are the example of conductors like metals, and insulators like rubber or plastic. So, the semiconductor lies between the conductor and insulator, and it has unique characteristics that it allows the characteristic that allows to control the flow of electric current, so in a very precise manner, so making them indispensable in electronics. And here are some common examples of electronic devices. So we have these electronic devices. So first we have the transistor. So perhaps it is the most fundamental semiconductor device. So this one is the example of transistor. So transistors are used for amplification, switching, and signal processing. So usually it has the three legs or three pins. So called the emitter, the base, and the collector. While for we also have diode. So this one is a diode. So this semiconductor device allows current to flow in one direction, so while blocking it in the opposite direction. And usually they are used in rectifiers, voltage regulators, and signal clippers. So we also have ICs. So usually in IC, they are considered complex semiconductor device that can contain thousands to billions of transistors and other components on a single chip. And usually they are considered as the brains of electronic devices and are used in computers, smartphones, microcontrollers, and many other applications. And the LEDs, LED or semiconductor device that emit lights. So when current flows through them, so they are usually used for lighting, displays, indicators, and optical communication. And these semiconductor device detect light and convert it into electrical current, and usually they are used in optical sensors and communication systems. Now, what is the role of electrons in a semiconductor? So, we have discussed earlier that electrons are the negatively charged particle of an atom, and the behavior of these electrons in a semiconductor is very crucial. As you can see in the figure, so this is four electrons in a valence shell of a semiconductor forming covalent bonds. This one. So it formed covalent bonds with other four atoms. So meaning in here, electrons are not free to move about the crystal lattice. So however, if we have thermal energy, so this thermal energy can create the few electron hole pairs resulting in weak conduction. So if this is the electron, and if an electron will leave or will transfer to other or jump into another level, so it forms a hole, and this hole is considered positive. So we can create a electron hole pairs. So it results into weak conduction. So at low temp, the electrons in the valence band are tightly bound to their atoms. But when we add energy, so meaning when we heat up or there is an applied voltage, some of these electrons jump to the conduction band. So it becomes charge carriers. So after this, we will tackle about valence band and conduction band. To understand how electrons behave in semiconductors, let us start with the concept of energy levels. So electrons in an atom occupy distinct energy levels or shells, so much like rungs on a ladder. And these energy levels are quantized, meaning electrons can only exist at specific energy values. So when energy is supplied to a semiconductor, it can excite electrons from lower energy level, to high. No, it's not right. Okay. So from low energy level to high energy level. So it absorbs energy, and this energy can come from various sources. So we can consider it as heat or an external electric field. And these excited electrons move to a higher energy levels, creating what we call the electron hole pairs. So remember that when an electron jumps from one level to another, meaning to up to higher level, the as electron jump to higher level, then it created a hole to this lower level. Okay, and this electron jump um, can also be if we jumped from low to high, then it absorbs energy. Now, if the electron will jump from high to low, then it emits energy. It emits energy through light. So it emits light. So for the band gap, basically the band gap, this is the energy difference between the highest energy level in the valence band. So we have two bands here, the valence and the conduction band. So the valence band, this is where the electrons are normally bound, and this is the highest energy level in the valence band, and the lowest energy level in the conduction band here. So this is where the electrons can move freely, and the size of the band, so this is the size of the band, this is called the band gap. And you can differentiate that the three properties. So we have the conductors, the metal, the semiconductor, and insulator. So as you can see, if we differentiate the band gap, so in conductors, um, we can see here that there is a actually this is overlapping. So there is an overlapping of the valence and the conduction band, and this allows electrons to move easily. um, on the other hand, for the insulator, it has a large band gap, as you can see here. So it has large band gap, and this makes electron movement to be impossible. While for the semiconductor, as you can see, so this is just in between. It has moderate band gap rather. So this moderate band gap can allow us to modify or control the electron flow. So in semiconductors, um, when electrons receive enough energy, so again, through heat or applied voltage, they jump across the band gap into the conduction band. So it becomes the charge carriers, and this jump enables the flow of electric current through the material. And this is crucial for semiconductor devices. We have discussed earlier that in semiconductors, the band gap is moderate in size. So if we have conduction band, this is the conduction band, and we have here the valence band. So it has a band gap of moderate in size. And here, we can say that we can manipulate the properties of this material. So this manipulation can be done through doping. So dope materials. So doping basically is to control the conductivity of the material. And how can we do that? So by introducing specific impurities. So these impurities, we can control its electrical properties. So what can we do here is we have two types of impurities. So we have n-type doping. So here we have n-type and the p-type. For the n-type, so the mechanism here is that it introduces extra electrons. So if we have a silicon atom, it has an extra electron here. So this extra electron becomes charge carriers and lowering the energy required for electrons to jump from the valence band to conduction band. So effectively decreasing the band gap. While for the p-type, so here the idea here is it has a electron vacancies or holes, extra holes. So which can enhance conductivity but in a different way. So holes can accept electrons and making it easier for them to move the conduction band, reducing to the effective band gap. So basically, here the doping, it can control the type and by precisely controlling the type and concentration of dopants. So engineers and physicists can tailor the electrical properties of semiconductors for a specific application. So again, such as transistors, diodes, and ICs. Now to discuss further the n-type doping. So here we have the n-type silicon. So it is created by introducing a pentavalent. So pentavalent means 5 valence electrons. So dopant atoms, this is a impurity. So this is a silicon pure crystal lattice. So here the common dopants for n-type silicon is phosphorus, arsenic, and antimony. So here this is a pentavalent type of dopant atom. So meaning this dopant atom can replace some of the silicon atom. So in this case, we have here, this is the dopant. And because they have one extra valence electrons, they become negatively charged ions. So ions with a net charge of -1. And this extra electron is not tightly bound to the nucleus and is free to move through the crystal lattice. So it is free to move to the crystal lattice. And this presence of this extra loosely bound electrons in the silicon lattice results in a surplus of negative charge carriers, making the n-type silicon an electron-rich material. And these electrons are called majority carriers. And because they are the most abundant charge carriers in an n-type silicon. Now we will understand the mechanism of an energy band of an n-type semiconductor. So we have here the valence band and the conduction band. So remember, the valence band is the lower energy band and the conduction band is the higher energy band. So here in the valence band, it is typically fully occupied by electrons. So in their most stable state. So electrons in the valence band are bound to individual atoms and do not contribute to its electrical conductivity. Now let's focus on the conduction band. Especially that in conduction band, this is where the electrical conductivity will be contributed. Okay, so in the conduction band, here this is empty or only partially filled with electrons, and these electrons in the conduction band are free to move through the crystal lattice. So the mechanism of the energy bond in an n-type semiconductor involves the introduction of donor impurity of the atom. So we have here the wherein we can found the extra electrons, and this creates donor levels just below the conduction band, and this just below the conduction band. So this is the donor level. So these donor levels make it easier for electrons to transition to the conduction band, resulting in a surplus of free electrons that contribute to the semiconductor's high electrical conductivity. So recall, the Fermi level is the energy level that defines the boundary between the valence band and the conduction band. So it represents the highest energy level at which electrons are most likely to be found at absolute zero temperature. So the position of the Fermi level in the energy band diagram depends on the doping of the semiconductor. And for the n-type, because of the introduction of donor impurities and their associated extra electrons, the Fermi level in an n-type semiconductor shifts closer to the conduction band. So this becomes the new higher Fermi level. And as a result, there are more electrons available in the conduction band for electrical conduction, making the material a better conductor of electricity. So the electrons can easily jump to the conduction band. And the Fermi level adjustment occurs to maintain charge neutrality in the material, and the concentration of electrons in the conduction band is roughly equal to the concentration of positively charged donor ions of the pentavalent material created by the dopant atoms. So this shifts of the Fermi level towards the conduction band, and which creates a surplus of electrons, making the material the n-type. Now for the p-type semiconductor, p-type, so this is a kind of semiconductor that has intentionally doped with specific impurities to increase the number of holes. So this hole is the positive charge carriers in the crystal lattice. So p-type doping. So this is created through introducing a trivalent or three valence electron. So this is the dopant atom, and into a pure silicon crystal lattice. So common dopants for p-type silicon are the boron and the aluminum. So these dopant atoms replace some of the silicon atoms in the crystal structure, and because they have one less valence electron than silicon, this one, so these create a hole or empty space in the crystal lattice, and these holes act as positive charge carriers. So the presence of these holes in the silicon lattice results in the surplus of of positive charge. So here we can say that this is a hole-rich material. And remember, holes are essentially vacancies in the valence band where electrons could have been. So when an electron moves from one atom to another, it leaves a hole behind. So here, meaning this is where should electron could have been, but the electron jumps to anywhere to another level. So for the p-type energy band, um, so here, so unlike the n-type, right? So here, again, this is the conduction bond and the valence bond. So their difference is the dopant atoms in a p-type semiconductor have one less valence electron than silicon. So as a result, they create energy levels just above the valence band, called the acceptor level. And these positively charged acceptor ions create localized energy states in the band gap just above the valence band. And when an external energy source such as thermal energy or an applied voltage is provided, holes from the valence band can easily gain energy to move into the acceptor level. And these holes in the acceptor levels create mobile. So we have mobile holes which can move through the crystal lattice and contribute to the electrical conductivity of the semiconductor. And the presence of a high concentration of holes in the valence band is what gives p-type semiconductors their hole-dominated electrical conductivity properties. And you can also see here that we now have a new lower Fermi level for the p-type semiconductor. So we have learned earlier about the p-type and n-type semiconductor material. Now we will learn about p-n junction. Specifically, this is an unbiased p-n junction. So when a p-type and n-type semiconductor are brought into contact to form a p-n junction, so electrons from the n side, so we have here the electrons, the negatively charged particle. So electrons from the n side and holes from the p side begin to diffuse across the junction due to their concentration gradients. So as electrons from the n side move into the p side and combined with holes, they create negative ions. So here, they create negative ions in the n side and positive ions in the p side. So along the junction. So this process leaves behind immobile, uncompensated positive and negative charges, creating an electric field that opposes further diffusion of charge carriers. So there is no diffusion. So it opposes the diffusion of charge carriers between the two. So the region near the junction where charge carriers have diffused away is called the depletion region. So this is the depletion region. And it contains immobile ions and acts as a barrier to the flow of charge carriers. So eventually, an equilibrium is reached where the rate of electron-hole recombination in the depletion region equals the rate of carrier diffusion. So at this point, no net movement of charge carriers occurs across the junction. So here, there is no net movement will occur. So the electric field in the depletion region results in a potential difference known as the barrier potential. So we have the barrier potential or the junction potential. So this opposes the further flow of charge carriers across the junction. So in a PN junction, the N side becomes the negatively charged and the P side becomes positively charged. Now to discuss the forward bias and the reverse bias of a PN junction. So in forward bias, applying a forward bias voltage to the PN junction means connecting the positive terminal of a voltage source to the P side and the negative terminal to the N side. So this external voltage reduces the barrier potential and allows electrons to flow from the N side to the P side and holes to flow from the P side to the N side. So you can see here, as a result, the depletion region narrows. It becomes narrow and the junction becomes conductive. So current can now flow through the junction in the direction of the applied voltage. While for the reverse bias, it is opposite. So we apply a reverse bias voltage, which means that connecting the positive terminal to the N side and the negative terminal to the P side. So as a result, this increases the barrier potential and widens the depletion region, making it less conductive. So in this configuration, only a very small leakage current, called the reverse bias current, can flow through the junction, and the majority of charge carriers are prevented from crossing the junction. So meaning there is no current flow. So in conclusion, PN junctions are fundamental building blocks for various semiconductor devices. So in diodes, they allow the control of current flow in one direction. So diodes allow current to flow in one direction. So one direction. And permitting current to pass in the forward bias condition and blocking it in the reverse bias condition. While for the bipolar junction transistors, PN junction are used to control the flow of electrons and holes, enabling amplification of electrical signals. And in solar panels, PN junctions are used to convert light energy into electrical energy by creating electron-hole pairs when photon strikes the semiconductor. Now we have covered the fundamental principles of semiconductors in this lecture, from their atomic structure and energy band theory to the formation and operation of PN junctions. So as we move forward in our exploration of semiconductor physics and its applications, remember that these fundamental concepts will serve as the building blocks for deeper insights into transistors, diodes, ICs, and more. So stay curious, keep learning, and embrace the endless possibilities that semiconductor technology has to offer. So, thank you for joining me in this lecture, and I look forward to our continued journey into the exciting world of semiconductors.